Good afternoon, everybody. So we'll try to restart the presentation just after the lunch. So I hope that everybody is awake. So this afternoon we will talk about behavioral models. So I don't know who of you already use this kind of models because it's not a new topic, but it's still a topic which is under discussion. So we'll present some of them this afternoon. So in the family of these models, in fact, to my point of view, we can see two different families for these behavioral models. The first one is more dedicated to unmatched devices, such as transistors. And when we are dealing with behavioral model for transistors, the aim is to use this model to design a circuit, such as a PA, for example. So we need to have some model capabilities, such as flexibility over load impedance and so on. So these models has to be accurate for different loading conditions, even in interpolated or extrapolated loading conditions. And the other family of models are rather dedicated to circuits, such as amplifiers. So when dealing with amplifiers, the need is not exactly the same. That is to say, we don't care about the influence of the loading impedance. We are much more dedicated to the model performances when we are using modulated signals, let's say wideband modulated signals, because this is a trend now to have wider and wider spectra. So here the needs are not exactly the same. So this presentation will mainly deal with this part, which is dedicated to how to extract a model for a PA. So when we use such a model, in fact, we will test different, we will not use the same measurements, for example. Indeed, for transistor, we will mainly do load pool measurement to locate where is the best area regarding the PIE or output power, for example. While for an amplifier, we will rather use some modulated signals, and we will assume that the PA works in near 50 ohm impedance conditions. So in order to extract the behavioral model of an amplifiers, in fact, we will test this circuit versus different frequency, versus different power level, and so on. And the wish is to extract a model which is accurate over all these measurement conditions. Unfortunately, when we are dealing with nonlinear device, there's some parasitic effect that takes place into the circuit, such as memory effect. So why we are calling this memory effect? In fact, because if we are dealing with a memory-less circuits, we can see that, for example, if we look at the gain characteristic versus the input power, we can have a significant instantaneous response. That is to say, for one power level, we will have a given gain and no several values. But if we are using modulated signals where we have an instantaneous variation of the envelope magnitude, in fact, rather than having just one response for a given input power, we can have different value. Instead of having just a straight line, we have a cloud of points like this. That is to say, the instantaneous response to a given signal is not just a function of the input signal, it's also a function of the past signals. And this is why we are calling this the memories effect, because we have to deal with all this memory inside the amplifiers. And unfortunately, these phenomena are quite complex. That is to say, we have long-term and short-term memory effect. We can have very fast memory effect, that is to say, the memory time is very short, while on the other side, we can have other phenomena where the memory time is much longer. And the aim of our model is to be able to predict the output response of an amplifier, whatever the modulation which is used, because by nature this modulation can't be known if we want a model which, a generic model, let's say. So here the aim is to extract a model for a PA and to launch a simulation where we will be able to observe the main figures of merit, such as ACPR or EVM characteristics, which are typically obtained with modulated signals. So how to extract a model which is able to reproduce all these figures of merit with a good level of accuracy? If we look into the amplifiers, in fact, we can see that we will have different stage. For example, if we have multi-stage power amplifiers and so on. And we also have some matching circuits. We have some biasing circuits and so on. And if we look at the short time constant, that is to say the high frequency memory effect, in fact, they are caused by, for example, the matching circuit RF response. We can have a slope of the matching circuit response versus the frequency. And because if we are using a wideband modulated signal, we will trigger this slope and we will create some nonlinearities regarding the output signal. And these effects are mainly caused by the high frequency memory effect. So it could be linked to the matching circuit, but it can also link to the transistor response, which usually have a decreasing gain response as a function of the frequency. And this causes these nonlinear distortions. On the other side, we can see that we have long-time distortion, long-time constant distortions that can be caused by the thermal effects. For example, if you are amplifying a modulated signal, if you are rather at a low power value, while you have a high consumption power, you will hit your amplifier. On the other side, if you are at the peak output power, the most part of this consumed power is converted into useful RF power, so the temperature is lower. So when you are using a modulated signal, you are hitting and decreasing the temperature dynamically of your amplifier, and this causes some long-term constant that could distort the output response. It could be the thermal effect, it could be also linked to trapping effect, because the time constant, mostly in the latest technologies such as gallium nitride, also had this parasitic effect. And you could also have some intermodulation product, low frequency intermodulation product that can go into the biasing circuits and create an unwanted modulation on the bias voltage that will bias the transistors. And it will also create some distortions. And it could be even worse if you also have some external circuits such as gain control circuits and so on. So in fact, we can have in one amplifier, we can have high frequency memory effect, low frequency memory effect, and the worst is that we can also have some coupling effect between all these phenomena. So it's very tough to extract a model which is able to take into account all these effects simultaneously. And we do not pretend to have a solution, a push-button solution on this. So in order to deal with all these phenomena, we have developed a software which is, let's say, a bridge between the measurement world and the simulation world. That is to say, we will drive a measurement bench that will extract first the high frequency characteristic of the power amplifier. So it's basic power sweep, different power level, different frequency, and we will probe the amplifier response within this boundary for a given power range and a given frequency range. On top of this measurement, we can apply some post-processing in order to smooth the data, which could be a very important step before extracting the model, because if you have noisy data taken from the measurements, then it can create some artifacts in the model which are not wanted. So this part is for the high frequency. And we can also have an interface that will use, let's say, time domain measurement, like pulse profiling measurement. For example, we will send a pulse on the amplifiers, and we will measure the response to this pulse in time domain. And we will convert this time domain response into a frequency response in order to see what is the behaviors of the kernels of these models, mostly dedicated to the low frequency memory effect. So in order to evaluate the added value of such a model, we made a benchmark using a classic behavioral model, which is a polyharmonic distortion model, which is very well known. For example, in a VSS, you have the S functions. And we also use the multi-harmonic Volterra model, which is our model, in fact. here in order to see what are the improvements bring by these models. So we did this exercise. Not it could be used with a measurement bench. That is to say, you can plug your amplifier on the measurement bench and extract the data. But it can be also a tool in order to simplify a model. For example, if you want to design a circuit with 1,000 amplifiers, you will not launch a simulation with 1,000 models of your PA defined at the circuit level. So it's to simplify the simulation. So you can even use an amplifier which has been designed in a circuit simulator, and using the data provided by this simulation, circuit level simulation, in order to extract your behavioral models. And this is what we have done here, in fact. And we will use this, we have done this exercise for a given amplifier. So here it was a common emitter amplifier, a very classic configuration. And the aim was to evaluate the improvement bring by this approach over a PhD, especially when we are looking at the figure of merits of modulated signals. So here is, we have used, in the circuit simulator, we have used a compact model, so it was a classic Gemenpulm NPN model of the transistor. And we biased this device here at 8 volts. And we have observed the characteristic of these amplifiers around 1.3 gigahertz. So here are the S parameters, for example. So we can see that in the RF bandwidth of interest, we have a slope of the S11 and S22 characteristic. It's not flat. That is to say, this characteristic can create some high frequency memory effect. That is to say, the RF response, really the RF response. So here, looking at S21, we also have a small slope, so even if it's not tremendous. So using this circuit, we can launch some harmonic balance simulation in order to evaluate the output power and the gain response different versus the input power. So, okay, we can obtain some characteristic like this ones. We can also evaluate the AM/PM characteristics. So here we can see that we have a sharp variation of the phase variation versus input power. And this will also create some high frequency memory effect. So even if we have not done the simulation yet, we can already see that we will have some distortions. Now, if we want to think about what can be the source of the low frequency memory effect, for example, we can observe the impedance seen on the source and the load side, but measured at very low frequency, in order to see what is the response, the frequency response of the biasing circuits, for example, to see if it's flat or not. And if obviously if it's not flat, then we may suspect that we will have some distortion if we have some low frequency intermodulation product that goes into these circuits. So just few words, very few words about the model itself. So when we are dealing with polyharmonic distortion model, a classic model, in fact, so the concept is to say that if we inject a signal at a given port and at a given frequency, and if we, on top of this signal, we applied a small perturbation, we can see what is the influence of the input signal at a given harmonic on the output signals at the fundamental or harmonic frequencies. So, and we create a model of this amplifier using different kernels, for example. So we call them S, I, K, G, L, for example. So let's take an example. For example, if we are looking for S2211, we are observing the influence of the signal on port 1 at harmonic 1 over the signal on port 2 at harmonic 2. That is to say, the harmonic response, for example, versus the input power. So it could be S2211, which is, but it could be also the S2111, which is basically the S21 in linear conditions, if we simplify in linear conditions. So this is the basic PhD model theory. So what we did here, in fact, is that we tried, instead of having a model which is just given for one frequency and all the harmonics. We rather try to work with a modulated signal. That is to say, we applied on top of these kernels some integral here in order to make an integration of the model response over these kernels, which is a combination of the PhD approach, in fact, and the Volterra series together. So we create some Volterra series on the kernels of the models. And this way, we are able to take into account wideband behavior in the model. So we have done different simulation using this model. So we are using a 16 QAM signal. And we try to use this signal, but for different symbol rates. For example, we did some experiments from 20 kilohertz up to 5 megahertz. And we at different power level. And we try to observe what are the figure of merits depending on the model we are using, in fact. So let's start with a low symbol rate, 20 kilohertz, for example. We can see that with such a low symbol rate, whatever, so the original response, the reference response is a circuit simulation. But if we are using the two behavior models here, the PhD or the MHV, in fact, we can observe the response in time domain. We cannot see any difference. So both models are accurate with these conditions. If we look at the ACPR response, again, we can observe a perfect fit between all the three curves, the reference curve and the MHV and PhD response. Let's increase a bit the symbol rate up to 500 kilohertz. And we can already observe some deviation between the circuit response in red and the static model with no memory, which is the blue curve here with the PhD. And here we can observe that these responses can be also observed in looking at the output spectrum, for example. But we can try this and push the limit at upper modulation rate. We will see that in the next slide. So again, just before going to this next slide, we can see that when we have modulated signals, in fact, because of the RF matching circuit response between versus the frequency, we will create high frequency memory effect. And some of the low frequency intermodulation can go down up here to into the biasing circuits that will create low frequency modulation. And this is why we will create some distortions that will depend on the symbol rate. So if we push again this one, we can observe that the difference between the reference circuit, the red curve, and the blue curve, which is a memory-less model, becomes higher. And we have done this for higher symbol rate again, 1 megahertz, for example, and we can see that the difference now is increasing again and again. So if you want to plot the constellation, the IQ constellation following this curve, it's rather better to use a memory model than a memory-less model. And we can observe some ACPR spectral regrowth, which were not taken into account by the memory-less model as well. And so here we can, so it's not visible here, but we can also observe some other phenomena, for example, such as the dissymmetry between the left and right ACPR characteristics when we take into account this memory effect. So here it's just a few words to say that it's important to take into account this effect, in fact, because if we want to have an accurate simulation regarding a very important figure of merit regarding the linearity, we really need to take care about all this intermodulation product at, and memory effect at high frequency and low frequency simultaneously. So here we are not in a real life operating conditions because the VM is very high, but this exercise has been done just to show the added value, in fact, of this model here is the difference between the two approaches. Okay, so this is the conclusion. So I split my presentation in two different parts, in fact. There's one part which is a PowerPoint presentation about the concept, just to present you the approach. And the second part is more about a video record of the model extraction from the measurement and the model use into the simulator. So just to give you some few information how it works, in fact, when we use these solutions. So just to conclude this PowerPoint presentation, we can say that when there's no memory effect triggered because the symbol rate is very low, then you don't care about having such a complex model, in fact. But if you extend the bandwidth of your RF signal, like in modern telecommunication format, then it starts to be important to take into account all this memory effect, especially if you want to simulate very important figure of merits for the linearity. So I will try to manage this dynamically. So this presentation is split in two different parts. First step is the model extraction, how we use the measurement data or the simulation data to extract the model, and then how we can use this model into a simulator. So let's start with the extraction of the amplifier MHV model. So we have an interface which is dedicated to this model. So we can either deal with only with we can extract a model only for short-term memory effect, high-frequency memory effect, or we can try to extract a model that will take into account both low-frequency and high-frequency memory effect. So here it's the case. So we have a dedicated interface where we will load the measurement file. So it can be XINP file, for example, which are well known for behavior models. So, and loading this file, in fact, we will see the different kernels of the model. So you can choose here the different kernels. So it's a mathematical approach. So again, S1111, it's influence of signal on port 1 at harmonic 1 and port 1 harmonic 1. So in linear condition, it's the S corresponds to the S11. But here we plot this figure of merit in the frequency bandwidth of interest around the carrier. And we can also plot this one versus different power level. And we can visualize these kernels in the opposite direction. That is to say, we can visualize the S11 versus RF power for different frequency level. So in fact, it can be useful to just feel how the model behave or the data behave before the model extraction. Because if you have some noisy data, for example, then it will be hard to use this model into a simulator, especially if you have hundreds of models that working together. So we need to have smooth variations. So we can observe the magnitude, but we can also have the phase for these model kernels. We can also apply some post-processing. That is to say, we can filter the data for a given frequency bandwidth or for a given power range. Once we have done this post-processing, we can identify the model. That is to say, we will try to fit some functions that will reproduce the behaviors of the model for each kernels. So we are also able to observe the error between the model and the original data if needed. And we can try to visualize what are the different kernels. So here it has been done only in a 400 megahertz bandwidth around the carrier. So for example, here we have the, let's say in linear conditions, the S21. So this is the S21 in the RF bandwidth of interest. This is where we will use our modulated signals. Okay, so we can see that we have a good behavior here. So now we will shift to the low frequency memory effect model. So as we said, in fact, here it's not a frequency measurement domain. We will take a time domain measurement. That is to say, if we made a simulation, here we will visualize the time domain's response, and we will convert this time domain response into a frequency domain response. And we will observe the behavior of this low frequency memory effect that takes place at low frequency. And for example, here we can observe that the main influence is in the 200 megahertz bandwidth here. That is to say, there's no need to take into account all this data basically into the model, because it will increase the weight of the model without bringing any benefits. Okay. So, and again here, because it was this data are taken from measurements, so we can also apply some post-processing. So for example, we can relax the number of data embedded into the model, and we can split the measurements in order to strengthen the model and its robustness into a simulator. So for example, here the red data have been split in comparison with the green original measurement data. And we can observe the different kernels again, but here it's different from it's really the low frequency kernels which has been done here. And if we look at this data, for example, so we have S2211, which is the harmonic response of the amplifier. We inject a fundamental signal, and we have some harmonic tones which are generated. So obviously, if we are in linear conditions, there's no harmonic power. So it's just noise. So we don't want to have all this data into the model. So it's important to filter this noisy data. So we can we can check these boxes, for example. So we will separate the measurement between the fundamental and the harmonic tones, so that the model will take into account only the harmonic response over a certain threshold. There's no need to have the data from minus 10 dBm, for example. We'll just take the data starting at 5 dBm. And so we are able to reduce significantly the noise into the model. So now we have our model. We can start the extraction of the low frequency memory model, just to check that the functions we have on this model fits well the measurements we had. So let's say the post-processing we made. So we can observe some deviation here, which are mainly a response to the long-term memory effect. We can see that we are able to fit the response in the bandwidth of interest. And then we just have to select the file name to export this model to the simulator. Okay. My model. All right. So now we will see how to use this model in a simulator. And here this exercise has been done with VSS. So we will load a template, basically, where we will be able, so it's a template, it's a very basic template. It's not a sophisticated system simulation. We just have the power amplifier, basically. So we will, it's just to highlight that we can simulate this model into VSS. So we drag and drop the model here. We'll connect the model to the template. And we will launch a simulation in order to observe the figure of merit, the important figures of merits. So there's two different files with different headers. So we have one file which is already dedicated to the high frequency memory effect, and we have a second file which is rather dedicated to low frequency memory effect. So we have a link where we will read all these kernels, and then we will be able to launch a simulation and observe the figures of merit, such as EVM, for example, for different power for different power level. We can observe the data also in time domain and visualize ACPR or EVM characteristics. And that is for this small video record. Thank you for your attention.